Okay, so for our second part on probability as it relates to biostatistics and the usage in research studies and epidemiological investigations, we're going to focus a little bit on how the p-value is used in research. And I've got this little picture here of the gravestone to the p-value because some people have criticized this approach, and maybe it's because some people have abused this approach, but yet there are still some that maybe worship this approach, and there's a little bit of a balance between the two that we'll get into here at the end as to why some people are so heavily critical of this approach, and yet why so many people actually love this approach so much and use it so much. So we'll get into that, but first it requires us to have a greater understanding of the p-value. So back to a review. So the p-value, as I view it, is a level that we set as researchers or statisticians as the probability level or threshold using our sample of data of the true population that we set in advance, ideally, in which we may choose to reject a null hypothesis and therefore assume a real or statistically significant effect or difference truly exists. So what that means is that when we set our alpha at 0.05, that means that if we have a p-value of 0.04, 03, 02 on our statistical models or our statistical tests, that means that we're willing to accept up to a 5% probability of error, where we may suggest that a difference exists when in fact it may not exist. So how much are we willing to accept? And I think that that varies with the research question, and whether you want to err on the side of caution or whether or not you want to err on the side of something where caution may cause you a lot of financial burden over something fairly trivial, or where there's not a lot of data to support it or a good biological basis for the hypothesis at play. So setting that alpha level of 0.05, it's kind of arbitrary. A lot of statisticians just set it at 0.05. And whether or not that's appropriate for every research question's, I think, subject to debate. So let's explore this alpha level a little further. Maybe we can make a little more sense of it. So if we set an alpha level of 0.01, alpha of 0.01, that means that instead of being willing to accept a 5% probability of erring, we're willing to accept a 1% probability of erring, indicating that a difference or an effect exists when, in fact, it may not exist. So this is kind of a higher threshold for our data or our data analysis to meet to suggest that a significant difference or effect is in fact present. You may not want that. You may want something with a lower threshold. You may want to go the other way. But usually we don't often see alpha values much lower than 0.10. Generally, they're overwhelmingly set at 0.05 or 0.01, 0.05 being the most common. So in this example also, when you have the opposite of alpha, kind of like 1 minus alpha. So if we've got an alpha of 0.01, that means we're willing to accept this 1% chance of being wrong. But we also are indicating to the contrary that we believe that 99 times out of 100 that there is in fact a true difference. Now there's a 1% or less chance that, or 1% chance or less that we could be wrong, but 99% of the time, based upon our estimates from our data set, we would suggest that a true difference or effect would in fact exist. So now, if we had our alpha set at 0.05 and we did some sort of test, which you're going to be doing here in this class shortly, or you're already seeing it through the interpretation of odds ratios from the actual papers. If we observe a p-value of 0.002, that is clearly below 0.05. So when we do t-testing or chi-square testing or whatever it might be, when we see p-values of 0.002, that tells us that that's less than 0.05. So we have the ability at this point to say that there is a statistically significant effect, and we reject a null hypothesis that says nothing is going on, that there is no difference. If we had a p-value of 0.02, we accept an alternate hypothesis that suggests that there is an effect or something going on, which is the opposite of rejecting a null hypothesis, or which is the same as rejecting a null hypothesis. It's the opposite of accepting the null. A null hypothesis is one in which it says that there's something equal or no effect. Something, something is nothing's going on. That's kind of our null hypothesis. Here, if we had a p-value of 0.02, we reject the null hypothesis that nothing's going on, and we have greater than 95% certainty that there is a true statistically significant effect or difference. If we observed a p-value of 0.02, since 0.002 is below our alpha level of 0.05, we would presume that this effect or this result is statistically significant. Some people will just call it a significant result or a significant effect or a significant interaction or a significant whatever it is that you're working with. Also, maybe we didn't have our alpha set at 0.05. Maybe we set our alpha level at 0.01. Since 0.002 is less than 0.01, that would be significant. In fact, we would, if we set it at 0.001, we could take this down all the way to like 0.005 and it would still meet it, because 0.002 is less than 0.005. So we would be, if it was 0.02, we'd actually be kind of like thinking that we're 99.8% sure that this effect is actually true based upon the evidence that we have through our study design. Now, if you got a flawed study design, all this is kind of rubbish. So, but if you've got a really good study design that really samples the true population and ideally as random as possible or in a way that reflects the true population, then yeah, this stuff is pretty helpful. But if your study design is rubbish from the beginning, all this goes out the window anyways. So that's all on the slides. Now let's actually take it to an actual scientific paper. So we're going to look at this recent article from the journal Addictive Behaviors in January of 2018 from these authors at the University of Texas at Austin. And they're looking at e-cigarette use by itself, whether or not it is responsible or at least associated with cigarette initiation, when people first smoke their first cigarette. So it's not saying that it causes it, but it is examining whether or not it's associated with the initiation or the first use of cigarettes. So we have some people, when they get to college, all they've ever used were e-cigarettes. Maybe they were sneaking them in school, grade school, or maybe it was easier for them to get online when they were in middle school or high school, and then they get to college. What happens? So we start looking at their data, and I'll just use this one to get us started. So I'm going to zoom in on Table 2 here. Table 2 seemed to have it. So Table 2 provides descriptive statistics for their entire sample and differences in their predictive variables between college students who started cigarette use over the 1.5-year study period and those who did not. So we have everybody. We have those who started smoking, those who did not. So University of Texas at Austin, I believe, is where this study occurred. Smoking among UT Austin students isn't as common as in the rest of the state. UT Austin is Academically, a pretty strong institution. It also costs a little bit more. We know cigarette use is higher among low-income persons. Students go to UT Austin, usually have a little bit more money, so they're less likely to start smoking. Needless to say, 282 started smoking out of the 2,558. And when we look to see if there's a difference in the age of the people who started smoking versus those who did not, we see a p-value of 0.757. So this average age difference, they did a t-test, showed no statistically significant difference. With regards to the male gender versus presumably the female gender, they did a chi-square test. 35% of the smokers are guys versus 31.8%. Of the guys who did. Okay, so we're comparing guys who started smoking versus guys who did not start smoking. So of the people who started smoking, 35.8% versus 31.8%, no significant difference. When they look at all these different races and do a chi-square test, p-value 0.236, no significant differences. I guess they were looking at multiple universities around Texas, not just UT Austin, so I may have erred in my interpretation there of where these students came from. No difference on whether or not they were at a four-year institution or not, p-value of 0.414. I'm not for sure what the variable cigarette susceptibility was, but people who started smoking obviously had a statistically significant difference between those who did not. 16.7% of those who started had susceptibility, whatever that scoring metric was, maybe a family history or something of that. So let's look at family history. If the family members used any tobacco, 61% of the kids had a family who used tobacco if they started smoking versus 51.5% of the kids who didn't start smoking. So there was a significant difference there. P is less than 0.05. So we would say that there was a significant difference between them. Family origin does seem to matter. What about if they had friends who used cigarettes? So the overall population, 52.7% of the kids studied or people studied had friends who used cigarettes. Among those who initiated smoking, 64.5% of them had friends who smoked, versus 51.2% who had friends who smoked, but these people did not initiate smoking. So p-value 0.001, and it's actually less than 0.001, so very strongly significant, clearly below 0.05. Other tobacco use, if they've ever used something other than cigarettes, or I guess e-cigarettes, like chewing tobacco or something, these folks 58.2% versus these folks 28.3%. Maybe hookah, whatever. So again, strongly significant difference. And then lastly, the crux of their study, 22.2% of the whole population ever had used e-cigarettes. But when you look at people who started during this 1.5-year follow-up, 40% of them had used e-cigarettes before versus 19.9% in the population that didn't start. So nearly double. And by chi-square test here, or x squared, that stands for the Greek letter chi squared, we see the p-value is less than 0.001, which is clearly below 0.05, which in fact means that we're more than 99.9% certain that there is a significant effect, or at least a significant association between e-cigarette use and initiating tobacco smoke. So that's a little introduction into the p-value approach. Now there's this kind of funny article here with the picture that kind of talks a little bit about p-values. Recently, the American Statistical Association weighed in on certain journals, like this particular journal, Basic and Applied Social Psychology, banning hypothesis testing and kind of the p-value approach from publication in their articles. ASA disagrees with them a little bit, but they do indicate some kind of rules for when and how to use p-values, and I can provide this article as a follow-up on Blackboard if you're interested. So that concludes the last bit here on p-values and probability. Thanks.